Sounds like you guys are discussing magnetic fields.
Yeah.
Also sounds like you're learning the right hand rule. For your thumb is the direction of the current, your fingers wrap around on the right hand. If the current is flowing in a coil, then your thumb gives you the direction of the field and all that kind of stuff. Don't know if you guys know that one yet, but if you don't, you will.
Probably learned that in second grade.
Probably did actually. Seems like something I would talk about. All right. When we were talking about magnetically coupled circuits and all that jazz. Okay, when we left off on Friday, we had performed Kirchhoff's current law at the emitter node of our small signal model for our common emitter amplifier, including emitter degeneration and early effects. So what we're going to do now is we're going to apply Kirchhoff's current law at the collector terminal. So let's scroll back up here and see what we've got. So we should also have three currents that are leaving our collector terminal. We are going to have our dependent source current GMV pi. We're also going to have the current flowing through our early effect resistance R naught, as well as the current flowing through our collector resistance R sub C. So performing KCL at our collector is going to look something like this. My stylus will write. So first I'm going to have the GM V pi term. And we already figured out that V pi is the same thing as Vn minus Ve. So I'm just going to substitute that in as well. Then we'll have V out minus Ve divided by R naught. And then V out over RC. Set this equal to 0. And now what I'm going to do is effectively find a relationship for VE in terms of V in and V out, so that I can substitute that relationship here for VE, and we'll just have a single equation, or I guess really here, a single equation that's relating V in and V out, and that'll be enough with a crap ton of messy algebra, which we're going to gloss over, to figure out what our input-output relationship for this amplifier is. Okay. So first thing I can see is that I have a factor of Vn just multiplied by my transconductance Gm. Then I have V out being multiplied by a factor of 1 over R naught plus 1 over RE. Excuse me, that's 1 over RC. And then this is equal to VE times a factor of 1 over R naught plus GM. And so now I have voltages being multiplied by conductances, and so we can treat those conductances as the reciprocal of resistances. And what we wind up finding is that our emitter voltage, VE, is just going to be Vn times Gm times R naught in parallel with 1 over Gm plus V out times the ratio of R naught in parallel with 1 over Gm divided by R naught in parallel with RC. Okay. So just to be clear here, all I did was recognize that this term that's being multiplied by VE looks like the reciprocal of R naught in parallel with 1 over GM. Multiplied both sides through by that, so that's why I have an R naught in parallel with 1 over GM here, and an R naught in parallel with 1 over GM here. GM just looks like GM, 1 over R naught plus 1 over RC looks like the reciprocal of R naught in parallel with RC, which is why it's down here in the denominator. Okay. So now I have two equations and I can smash them together. Just doing simple substitution. And we're going to get something horrifying. So substituting two into one yields the following result. And I'm literally just skipping to the end here because I've shown you what I'm doing. All of the subsequent steps are just algebra and there's nothing pretty or informative about it. So our voltage gain winds up being negative. Let's start with our numerator. So this is R naught times R naught in parallel with RC times R pi in parallel with R naught in parallel with RE in parallel with 1 over GM minus GM R naught times R pi in parallel with 1 over GM times R naught in parallel with 1 over GM times R naught in parallel with RC. Now for our denominator, equally as gross, we have R pi in parallel with 1 over GM, R naught in parallel with RC, R pi in parallel with R naught in parallel with RE in parallel with 1 over GM minus R naught times R pi in parallel with 1 over GM times R naught in parallel with 1 over GM. Close things out there. So this is what things look like with the early effect included and emitter generation. And this is horrifyingly gross. And there's really not a whole hell of a lot of information that we can glean from this thing because it's so horrifyingly gross, right? It's just a big regurgitation of resistances and parallel multiplied by conductances all over the damn place. This doesn't really tell us anything useful. So in order to figure out what role emitter degeneration plays, while this is formally correct, let's see what happens if we were to let R naught approach infinity. So if we didn't have the early effect included, this actually simplifies down to something that's still a bit annoying, but not too terribly bad. Which now I have to go through my notes and find. Give me just a second. So when R naught approaches infinity, And R naught will typically be the largest resistance of all of these resistors anyway. So it should usually be significantly larger than R pi, RE, RC, and 1 over GM is usually the smallest resistance you'll see. So under these conditions, our voltage gain becomes approximately equal to negative GM times RC times R pi in parallel with 1 over GM divided by a factor of RE plus R pi in parallel with 1 over GM. So this is something that we can work with. It's much smaller and therefore much easier to figure out what trends are occurring, okay? So how does this compare to a common emitter amplifier without emitter degeneration? Well, in the case of a common emitter amplifier without emitter degeneration, our gain was effectively just negative GM RC if R naught was also taken to trend towards infinity. So what we see is we have this other term that's a ratio, R pi in parallel with 1 over GM divided by RE plus R pi in parallel with 1 over GM. Looks vaguely voltage divider-ish, right? What is it doing? Well, it's making the gain smaller, right? There's no way that this ratio of R pi in parallel with 1 over GM divided by RE plus R pi in parallel with 1 over GM will ever be a number that's larger than 1. Literally impossible, right? So from a voltage gain perspective, emitter degeneration tends to reduce the overall voltage gain of our circuit, which in some applications is a good thing, and in some applications is a bad thing. If we're looking for pure, we want the largest gain possible, emitter degeneration is bad. If, however, we want to make sure that our amplifier has a wider linear range of input voltages that it can amplify without having any distortion occur, degeneration is a good thing, okay? What's really interesting, and we'll actually see this in electronics too, is even though there's no obvious feedback in this system, it actually behaves exactly like a negative feedback circuit. We'll talk about that significantly more in 336. So this circuit literally has the benefits of negative feedback without actually having a negative feedback network. So, all right, so that is our voltage gain. Now we've got to figure out input resistance and output resistance. We'll follow a similar thing. I'll derive it out fully and formally. It will be terrifyingly gross. Then we'll pair things back to see what's happening if we neglect R naught, which is really the troublemaker in all of this, and see how things trend. So now we will determine our input resistance. I'll go ahead and redraw our small signal model since it's been a minute since we've looked at it. So this test voltage here, I'm just going to call Vx. Here's our base. Here's R pi, V pi. GM V pi. R naught. Here is our emitter resistance RE. Collector terminal. RC, and here's where we're measuring our output voltage. And our ultimate goal here is to determine the ratio. I'm calling that IN, but let's call it IX just so that we're using the same subscript on both sides, right? So we're trying to find out what the ratio of Vx over Ix is, because that will by definition be our input resistance. Now, previously, when we did not have emitter degeneration, it was very easy to see that our input resistance was simply R pi. Now, there's some other resistance between the emitter and ground, and so that's going to effectively mess up our input resistance relationship. I say mess up from a calculation standpoint, but it actually has a purpose, okay, for a practical application. So we're going to do something pretty similar to what we did earlier. I'm going to perform KCL at the emitter node. So I'm going to say the currents flowing in must equal the current flowing out. There's only one M in emitter. So my current flowing in is IX. I also have a GM V pi flowing in. So that's going to look like GM times Vx minus VE. So let's call this voltage VE again. I'm also going to have in my notes, I choose to do this, so I'm just going to be consistent so I don't make a mistake. I'm going to call the voltage drop across that resistor RC. Instead of using V out, I'm just using VC. Honestly, not sure why I made that decision 2 years ago when I made these, but I did it, and I don't want to screw things up or confuse you, so I'm just going to be consistent. So that's going to look like VC minus VE over R naught. And this will all equal to VE over RE. And all I'm going to do now is just kind of lump terms together like we did before, right? So I have an IX with nothing being multiplied by it. I have a VX that's being multiplied by GM. I have VE, moving all of the VE terms to the left-hand side. They're all going to look negative. So that's why I pulled that negative sign out. And then I get a 1 over R naught plus 1 over RE plus GM. And then lastly, I have my VC term that's only multiplied by 1 over R naught. And this is equal to 0. And here's my first equation. Sorry. Sorry, looking at my notes for this one, it looks like I didn't go through things quite as formally as I had with the other ones when I went to my next page for looking at things. It looks like I actually solved it doing a different method. So I'm actually gonna, sorry for wasting your time here. I'm gonna scrap this and do it the way that I had before. Nothing wrong with that per se, but it comes out to be kind of doofy. So actually, let me scratch this thing out. So it looks like what I had done, and I apologize for not being as prepared as I like to be, is I wound up redrawing the circuit in a way that was a little bit easier to analyze. So what that entailed was effectively performing a source transformation on this guy right here, and then kind of stretching it out, looking like a circuits one level problem. So let me explain what I mean by that. So my voltage Vx remains completely unchanged. I'm going to put the resistance R pi up here. This is my voltage V pi. And so effectively this node is my base. And now this node is my emitter. Okay. So between the emitter and ground, I put that resistance RE like so. And I'm just tying my grounds together. Now, if I do a source transformation on that dependent current source in parallel with that resistor R naught, it's going to wind up looking like a dependent voltage source in series with that resistor R naught. So something like this, plus minus, where I'm going to have GM R naught times R voltage V pi. In series with resistor R naught. This node over here is my collector, and then between the collector and ground, I have my resistance RC. Okay. So before we start our analysis here, does anybody have any problem with how we got from our normal small signal model on top to this representation down here? Anything seem suspicious? Hopefully it all seems okay, because as best as I can tell, it's correct. Okay. So ultimately, we are still trying to just find the ratio of this voltage Vx to whatever current is leaving the positive polarity terminal. So it looks like effectively I did mesh. It's back for this one instance. We might use it one more time in the next 2 weeks. Okay. So I'm going to call this current I1. Now I'm going to call this current I2. Right. So applying KVL around mesh one. we wind up getting negative Vx plus R pi times I1 plus RE times I1 minus I2 is equal to 0. And then applying KVL around mesh 2, I got RE times I2 minus I1 plus GM R naught V pi plus R naught I2 plus RC times I2 is equal to 0. So now I'm going to play around with this second equation such that I find out what I2 is in terms of I1. So I can see that I have an RE times an I2 minus an RE times an I1 plus GM R naught. So V pi is just R pi times I1 using Ohm's law, so nothing fancy there. And then I have my R naught I2 and RC I2. Recognizing also that GM, let me do this out over here, beta is GMR pi. Right? Relationship that we had before, except that actually we just said R pi is equal to beta over GM. I'm just reorganizing that so that I can use beta instead of things. And so from here, I can say that I have I2 times a factor of R naught plus RC plus RE is equal to I1 times RE minus beta R naught. Everybody okay with that? All I've done is just move the I1 terms over to the other side of the equal sign and just lump things together. Now, from here, we can see that I2 is nothing more than I1 times RE minus beta R naught divided by R naught plus RE plus RC. And I can substitute this relationship back in up here. So that now I will have a relationship that only depends on Vx and I1 effectively. And the ratio of Vx to I1 is the resistance that we're looking for. So going back to our KVL at mesh 1 equation, that's going to look like Vx is equal to I1 times R pi plus RE minus RE times I2 which in turn would be I1 times R pi plus RE minus I1 times RE times RE minus beta R naught divided by R naught plus RE plus RC, or I1 times R pi plus RE minus RE times RE minus beta R naught divided by R naught plus RE plus RC. So now I can simply divide Vx by I1 and I have my input resistance, right? So Rn is just Vx over I1. So that's going to look like R pi plus RE minus RE times RE minus beta R naught over R naught plus RE plus RC. And then this next bit here comes from me just manipulating this expression, skipping a couple of steps. We wind up getting R pi plus 1 plus beta RE R naught divided by R naught plus RE plus RC. All right. So our input resistance has increased, right? When we did not have emitter degeneration, this came out to be just R pi. Now we're adding to that something else. And that something else is actually going to be particularly large, right? And I say it's particularly large because in my numerator here, I have a factor of 1 plus beta. So for a bad transistor, this would be a factor of in the ballpark of 50. For a good transistor, this might be a few hundred times the product of RE and R naught. So the emitter degeneration serves to make the input resistance of the amplifier very, very large. Okay. Now, when R naught is neglected, or when R naught goes to infinity, effectively, this simplifies just 1 plus beta times R, which I'll write that down specifically for you. So for R naught approaching infinity, Rn is approximately equal to R pi plus 1 plus beta Re. Right. So to this point, we have determined that emitter degeneration lowers our voltage gain, but in doing so, actually causes a pretty large increase in our input resistance. So for some applications where we're trying to connect a sensor that has a large input resistance, this is something that we might need. Okay. Now let's determine our output resistance. So I'm going to draw my small signal model. I'm grounding or turning off my input voltage, which is why my base terminal is going to be directly at ground. Here's R pi, V pi, GM V pi, in parallel with R naught. Here's RE. Here's RC. And then over here to the right, I'm applying my test source. So this is going to be the circuit that I'm analyzing here. Now, it should be quite obvious that IX is going to split, right? Some portion of it is going to flow down through this part right here, and that portion is literally just going to be VX over RC, and then whatever's left flows through the remainder of that network, okay? So keep that in the back of your head. All right, so a couple of things that we can sort out pretty quickly. First, we can use Ohm's law to determine what V pi is, okay? So I'm going to call the current flowing through here IX prime, okay? Where IX prime, or sorry, let me do it this way. IX is equal to VX divided by RC plus IX prime. And so I'm going to have this as VX divided by RC plus VX divided by what I'm going to call R out prime. So effectively, if I can figure out what the relationship between Vx and Ix prime is, that's just the resistance of everything to the left. And that resistance is very obviously just in parallel with this resistor RC. Okay. So if I look at this current Ix, we see that it's going to split between these two things, and then it's going to come back together. That current Ix double prime sees this resistor Re in parallel with this resistor R pi. The voltage V pi is just the voltage drop across those two resistors in parallel, and this current is flowing into the negative polarity terminal. Are we all okay with that? So we also have the relationship that V pi is equal to negative Ix prime times R pi in parallel with Re. So what I'm going to do now is I'm going to apply Kirchhoff's voltage law. So let me explicitly define the path that I'm applying KVL around. Okay. I'm going to start here, go across my voltage source, across this resistor, across this resistor, and then go to ground. So I'm starting at ground and I'm ending at ground. So this is a valid path by which to apply Kirchhoff's voltage law because I'm starting and I'm ending at the same node. So what I'll have is Vx is equal to the voltage drop across this resistor plus the voltage drop across that resistor. Okay. Nothing remotely crazy or fancy here, just circuits 1 level stuff applied to something a little gross looking, right? Another thing that I can do is I can notice that this current right here is just the current Ix prime minus GMV pi. Okay. So that I can find the voltage drop across that resistor R naught. I'm going to put in quotes here easily. So applying KVL, I wind up getting that Vx is equal to R naught times Ix prime minus GMV pi minus V pi. Anybody have any beef with that? Literally just saying this voltage drop is equal to this voltage drop plus this voltage drop. Now substituting things in. Okay. So that's going to look like R naught times Ix prime plus GM. Now I'm going to substitute in for V pi, or actually it was minus originally, but I'm substituting in for V pi, so that negative is going to look like a positive. Then I'm going to have R pi in parallel with RE times IX prime. Doing that exact same substitution, I'm going to wind up having plus R pi in parallel with RE times IX prime. Everybody still catching what I'm throwing here? All I've done is substitute this relationship in for V pi here and here. Now, everything on the right-hand side is in terms of Rx, or, excuse me, IX prime, right? So I can just factor all that business out. So that's going to look like IX prime times R naught times 1 plus GM R pi in parallel with RE plus R pi in parallel with RE. And from here, I can say that R out prime is just R naught times 1 plus GM times R pi in parallel with RE plus R pi in parallel with RE. And finally then, looking at this relationship right here, I can say that R out is equal to RC in parallel with R naught times 1 plus GM R pi in parallel with RE plus R pi in parallel with RE. So we can kind of see what's going on here as well, or what the effects of our degeneration are. Okay, so when we had a common emitter amplifier without emitter degeneration, our output resistance was just R naught in parallel with RC, right? We still have something in parallel with RC, but now it's this big guy right here. Well, this big guy over here on the right-hand side is R naught times a factor of 1 plus something. So that means this guy got larger, plus this portion over here. So the R naught side of things got significantly larger because it's being multiplied by a factor of 1 plus some number that's going to be positive. So realistically, in a amplifier that's, in a common emitter amplifier that's utilizing emitter degeneration, it's just going to make the output resistance look more like RC by itself, because we know that when we have two resistors in parallel, it's going to look closer to the smaller resistor. And RC will practically always be much smaller than all this jibber jabber over here on the left. So the output resistance remains largely unchanged, taking into account that R naught is usually much larger than RC to begin with. This is just reinforcing. The input resistance changed by a whole heck of a lot, right? We get a huge boost in input resistance. Our voltage gain gets a moderate decrease, okay? So those are the effects of emitter degeneration. Now, just for completeness' sake, so if we allow R naught to approach infinity, then our output resistance is approximately just equal to RC. So we're now at a point to where we know our voltage gain, our input resistance, and our output resistance for this amplifier with emitter degeneration. So we now have a new model that we can stick in to analyze more complicated circuits. Okay. So do we need to formally do that like we did the big problem the other day? We literally just represented this with an input resistance and then a dependent voltage source in series with the output resistance, and then use that as the model to do our analysis for the larger system. So I don't want to do that today because we already know how to do it. So instead, what I want to do for the next few minutes is look at MOSFETs, which will be really, really easy because it's effectively the exact same thing that we've already done. So actually, I take that back. Sorry. I do want to look at one quick thing here. We're not going to do any analysis whatsoever. I just want to talk to you about something. Okay. So here's VCC. Here's our resistor RC. That's going to be RE, but I'm going to leave it blank because I'm going to mess with it in a moment. Here's R1. Here's R2. Put ground down here. Here's CN. Here's R sig. Here's our signal voltage we're trying to amplify with this thing. Here's C out. Here's our load resistance RL that we're trying to drive. Here's our output voltage. So this is the circuit that I drew originally when we were talking about common emitter amplifiers. And this is the one that I said that we were going to skip doing any formal analysis of, because we effectively already know how the amplifier portion of this thing works. Okay. So what we saw when we actually included some emitter degeneration was, just to recap what I said a moment ago, an increased input resistance, roughly the same output resistance, and a decrease in the voltage gain. So what some people do, like if you're trying to maximize the gain of a common emitter amplifier, right? This resistor right here plays an important role in the DC biasing, but we can get rid of it for the AC portion of the circuit. Anybody have any thoughts on how we might do that? A capacitor, absolutely right. So one option that we might see is to literally just put a large capacitor, let's call it CE, in parallel with it, such that the capacitor is large enough to look like a short circuit at our frequency of interest, so that our DC bias circuit remains completely intact. But on the AC side of things, we don't see any of the downsides, so a reduction in gain caused by the emitter degeneration. We also don't get that increase in the input resistance either. A way to kind of split the baby, so to speak, is to actually split the resistor up into two different things. You guys have never heard the King Solomon thing of literally splitting a baby in half as a compromise? Read your Bible. So what you may also see is something like this. So let's call this guy RE1 and this call this guy RE2. And then you'll put your emitter capacitance here. Typically speaking, RE1 is smaller than RE2 so that we get the full effects of an emitter resistance in the DC biasing network, but we only have this small degeneration so that it doesn't greatly decrease our gain while still giving us a pretty significant boost to the input resistance of the amplifier portion. Now we can talk about MOSFETs. Just wanted to make you guys aware of little tricks and stuff that engineers do to maximize the performance of these things. All right. So the common source amplifier is the MOSFET version of a common emitter amplifier. Okay. Same basic layout. The only thing we're going to do is we're going to change the BJT into a MOSFET. Everything else is exactly the same. We also changed the labels on our resistors because we no longer have a collector, base, and emitter terminal. We now have a source, drain, and gate terminal, right? So big picture, we're looking at something like this. Here's VDD. Here's some resistor RS. Here's some resistor. Oh, I have that backwards. I'm sorry. RD should be up here and RS should be down here. Here's R1. Here's R2. CN. RSig. VSig. Out. And RL. So what I want us to do is to analyze this circuit straight from the jump. Under the constraint that channel length modulation can be neglected, just for the sake of it. So, how do you guys think we might do this? Sure. So let's start by looking at the small signal model for this whole thing. Okay. So from a small signal model perspective, I'm going to have my signal source, RSig, R1 in parallel with R2. Here's my gate terminal. This is a NMOS, so that should be VGS, sorry. Oh, actually, we're neglecting channel link modulation, so I can just leave that guy out. That should be RD, sorry. And it actually, sorry. Doing it in this way. So here's our small signal model. Does this help any? I think it did immensely. So let me explain why I think it helped immensely. Because this would be the exact same as the small signal model for the BJT amplifier, except that RPi has now been replaced by an open circuit. So we can literally just go back to our notes for how the transistor amplifier behaves as a BJT and see what happens with RPi as an open circuit. Because we use that. So effectively, we should already know how this part works. Because that looks to be identically the same to common emitter amplifier with emitter degeneration, where the early effect has been neglected. So the voltage gain of this block right here is this, except that RC now becomes RD, RE now becomes RS. What happens when I have RPi in parallel with 1 over GM? And RPi is infinity. Zero goes to 1 over GM. Right? Something small in parallel with something huge looks like something small. Okay. So I can take this thing right here. So for the bit that I have boxed in red, a moment ago we had AV is equal to negative GM let me find it. What did I do with the page that I'm looking for? Let me just scroll back up because all my stuff's out of order. So negative GM RC times RPi in parallel with 1 over GM. Negative GM RC times RPi in parallel with 1 over GM divided by RE plus RPi in parallel with 1 over GM, right? That's what we had. Now, this is going to look like negative GM. So where we had RC, we now have RD. Where we had RPi in parallel with 1 over GM, we just have 1 over GM. This is going to look like RS plus 1 over GM. There's our voltage gain of that part there in the middle. Our input resistance with the early effect neglected was R pi plus RE times beta plus 1. What's the input resistance of the part in red going to look like as a MOSFET? So first, beta isn't a thing for a MOSFET, so that's a little problematic. However, R pi being replaced by infinity means that it's just going to look like infinity. What's our out going to look like? So if we scroll back up here, R out could look like RC for the MOSFET, or excuse me, RC for the BJT, which will just be RD for the MOSFET. And from there, we can literally just put it together like we did previously, right? So now we'll have something that's looking like this. So this is the circuit that we're now analyzing, where Rn prime is infinity, R out prime is RD, and our voltage gain is, let's call this prime. This guy right here. I didn't even notice this until just now, but that GM and that GM. So from here, right, we could say that Vn is just going to be V sig times R1 in parallel with R2, that quantity in parallel with Rn prime, divided by R sig plus R1 in parallel with R2 in parallel with Rn prime, which actually just becomes V sig times R1 in parallel with R2 over R sig plus R1 in parallel with R2, because we know that R in prime is infinitely large. The out is just going to be AV prime times VN times RL over R out prime plus RL. So that's going to look like, I'm putting the GM in there just in case I need it. Negative GM R D times 1 over GM divided by RS plus 1 over GM. So that's my AV times RL over R out prime, which was RD plus RL. I'm putting my V in here. So to me, I have an RD times RL divided by an RD plus RL. So that looks like RD in parallel with RL. So just to be clear here, that's taking care of this part, and that part right there. And now I'm going to have times 1 over RS plus 1 over GM. So that's my relationship between V out and V in. So my voltage gain for the whole system is just V out over V in times V in over V sig becomes R1 in parallel with R2 over R sig plus R1 in parallel with R2, negative sign out front, RD in parallel with RL over RS plus 1 over GM. What should my input resistance be for the new thing? So R sig plus R1 parallel with R2. What should my output resistance for the system be? Anybody have any thoughts? What? It will be. Say that again, please. RD in parallel to RL. Absolutely right. Yes, ma'am. So what I boxed in red here is just the transistor amplifier portion. Okay? These quantities that I detailed in red are just for what's inside the box. And then we use those in this relation, right? So I can put the red box on here as well for what it's worth. So we just replaced that transistor amplifier portion with this equivalent circuit because it makes it very easy to analyze the system as a whole. Okay? So one of the best things about this class is also one of the worst things about this class. It is recognizing, have I seen this before? If so, we don't need to do it again. If I've seen it before and I know how it behaves, I can just plug an equivalent circuit into a larger, uglier thing and just go from that, which is all we are going to be doing. Until you catch on to that and become comfortable with it, you are going to have a miserable experience. Just to be very, very clear. More miserable than normal with me. Okay. So we're 3 minutes over, but actually I think we're a day ahead. Because this doesn't have to be hard. If we can understand how the basic little parts work, we can just use an easy to manipulate equivalent circuit and then connect the rest of it to that equivalent circuit and just figure out what's happening, okay? So we're going to spend, once again, the majority of our time on how the BJTs work, because the only difference between the MOSFET and the BJT from a small signal perspective is that the input resistance, or R pi, is infinitely large. Everything else works out exactly the same. So there, to me, is literally no point in actually doing a formal analysis because we can just look at the damn thing. Yes. Yeah. So I might ask you to do a circuit analysis type thing. So I might ask you to do an actual analysis for a MOSFET. I've given you the steps to show you how it's done for the BJT. So to do it for a MOSFET, all you would do is just follow the exact steps that I did, except that it should be easier because there's less crap to worry about. So that would be the quote unquote difficult problems. Would be, I ask you to derive the relationship for a MOSFET where you already know what it's supposed to be. What else? Yep. R out is RD. So for our BJT amplifier, when the early effect is neglected, our output resistance was just RC. If we look at where the hell did I draw the original circuit? Sweet mother of God. It's been a minute. For the MOSFET, that resistor is called RD. That's it.
Yeah. Then in the very last one, that's all out prime and all that.
Mm-hmm.
All out prime.
R out prime is RD. Yes. So let me, it's not quite clear apparently. Make smaller. There we go. Okay, so that we can see everything at the same time. These relationships in red. Why is it continuing to get smaller? I've walked it. These relationships in red are just for what is in the red box, right? So in the red box, the voltage gain So the ratio of the voltage at this node, if we were to call it V in, and the voltage at this node, if we were to call it V out, for a BJT with emitter degeneration, but also neglecting the early effect, would be this. Then I said, all right, so now I have a MOSFET. So everywhere I had R pi looks like infinity. Infinity in parallel with 1 over GM is just 1 over GM. Everywhere I had RC, I replaced it with RD. Everywhere I had RE, I replaced it with RS. This is the relationship for the input resistance of this portion of the amplifier, which looks like R pi plus RE times beta plus 1. For a MOSFET, because R pi is infinity, it just looks like an. For everything in the red box, the output resistance for the BJT just looks like RC, which for a MOSFET is RD. Then I did my analysis, and I used that very loosely, of the full circuit, right? So everything in the red box is literally everything in the red box from the previous diagram. I just no longer give a shit about there being a transistor there because I don't need it. I know what Rn is, I know what R out is, I know what my voltage gain is, okay? So for this part right here, all I'm doing is voltage division for this part over here on the left. For this part right here, all I'm doing is voltage division for this part on the right, and then I'm just substituting in the relationships. That's it. Same stuff down here. This is me just saying I can split the voltage gain to be V out over V in times V in over V sig, which comes out to be V out over V sig, which is the voltage gain for the entire system. For the input resistance, I was literally just looking at what resistance does this voltage source see as current leaves the positive polarity terminal and travels on its path to ground. It's going to see R sig in series with R1 in parallel with R2 in parallel with Rn prime. Since we know that Rn prime is infinitely large, it's just going to be R sig in series with R1 in parallel with R2, which is exactly what we got right here. To determine my output resistance, I would short this guy, which is going to look like nothing here, which means Vn is nothing, which means AB times Vn is nothing. So I have R out prime and RL prime in parallel. Since R out prime is RD, I saw RD in parallel with L prime. Whole thing done in minutes. All right. I'll stop ranting at you guys for today, and I will continue ranting at you guys on Wednesday.